When you take a tuning fork and do this, the prong of the fork vibrates and sets up a sound wave. And when this sound wave hits your eardrum, you can hear the note that is being played by the tuning fork. Now, it's easy enough to understand how tuning forks make sounds because you can see the vibrations. But how do computers make sounds? They don't vibrate, do they? No, but they can make other things vibrate. Every time a computer circuit switches on or off, there is a tiny increase or decrease in electric current. It's like a miniature heartbeat that sends out a miniature electrical pulse. This pulse is much too weak to generate any sound on its own, but it can be fed into a tiny device called a transducer to produce a tiny sound. But if we want a louder sound, we must first make the pulse larger. We must amplify it. And this is simple to do because our computer monitor or TV set comes already equipped with an amplifier. If we feed the computer's pulse into this amplifier, it will then be made large enough to cause a loudspeaker to vibrate and therefore create a sound wave that we can hear. So, provided that your computer is hooked into an amplifier and a loudspeaker, simply by turning a circuit on or off, you will be able to make a blip sound. Of course, this blip can hardly be called music, but if you tell the computer to switch a circuit on and off more and more rapidly, it will produce a faster and faster string of blips, and eventually you will hear a musical note. The more frequent the blips, the higher the note, and the less frequent the blips, the lower the note, which is why the highness or lowness of a note is called its frequency. For example, if we get the computer to turn a circuit on and off precisely 440 times a second, we will hear 440 blips per second, which happens to be the frequency of the musical note A. And this is exactly how a tuning fork, or a piano, or a guitar, or a trumpet also produces the musical note A, or any other note for that matter. It's all based on vibrations. So your computer can not only give you good words, and good numbers, and good pictures, it can also give you good vibrations. Someone once said that architecture is frozen music. And this is more than just a pretty phrase, because if we take the sounds produced by different musical instruments and freeze them, we will see that frozen music does look rather like architecture. Some sound waves look like a row of pyramids, some like a string of mud huts, and others are a jumble of all sorts of shapes and sizes. Now let's take a typical computer sound and freeze that. A row of little boxes. It looks as boring and repetitive as it sounds. All the boxes are the same shape. The waveforms are all square, and they are all the same size. There's no variation in their volume. This is because the switching on and off of a computer circuit can only produce sound waves that are either completely on or completely off. In order to improve the quality of computer sound, you need to add a music synthesizer chip. This synthesizer can create a range of waveforms, from sawtooth waves to triangular waves to mellow sine waves. It can also vary the volume of these waves, not just to sound louder or softer, but also to give each note an individual contour or sound envelope. This enables you to imitate a guitar, for example, whose notes have a waveform like this and an envelope like this, which starts quickly and fades quickly. Or a trumpet, which produces a waveform like this and an envelope like this, which starts slowly but can be sustained for a long time. And that's how, by manipulating various combinations of different waveforms and envelopes, a computer equipped with a music synthesizer can synthesize or put together the basic elements of any sound you like, so that you can turn your computer into a flute, or a violin, or a xylophone, or some instrument that no one's ever thought of before. There's no limit to the new forms of musical architecture that you can dream of.